Hmm. Alrighty, so today we are going to be talking about cache memory. Um let's do this real quick. Let me just share my screen. Okay, alrighty. Here we are. Okay, alrighty. This is lecture A. We are talking about caches today. We'll be briefing over them. First thing that I wanted to introduce today is that the introduction to caches, cache terminology, the cache associativity, cache misses and performance, cache optimization, as well as some examples and case studies, and then summarize all of that up in today's lecture. It shouldn't be too long, so let's go ahead and start into it. Just a quick introduction into cache. Over here on the right, we have a diagram that just like it shows what it is. We have input outputs going back and forth into a main memory and a secondary memory. Then from the main memory, it branches off to two, a CPU and a cache memory. Cache memory is where everything that we're going to be discussing today is going to happen. So like we said, just on the mainframe, have our main memory, inputs, outputs, and secondary memories, they all move around. And then the cache memory comes into between the CPU and the main memory as well. Without further ado, there are two principles of locality. There's a temporal locality and there's also a spatial locality. What are they? And temporal is if an item is referenced, it will tend to be referenced again soon. As for a spatial, if an item is referenced, items whose addresses are close by tend to be referenced soon. So they gotta be close by so that they be referenced. That's the difference between a temporal and a spatial. Um, what is also the difference between a cache and a main memory? Just like how it is between like a DRAM and a SRAM. A DRAM is a regular main memory, just like we just discussed in lecture 7 last week. And an SRAM is a cache memory. An SRAM is faster, but has a lower bit density, and it stores frequently assisted data, whereas the DRAM is higher bit density, poor latency, and has more cycles in order to access. Next, we'll be talking about cache terminology. So there's a hit rate, hit time, miss rate, miss penalty, and also average memory access time. So what is a hit? A hit data appears in some blocks in the cache. A hit rate is the fraction of the memory access found in the cache. A hit time is the time to find data in the cache, and miss rate is one hit rate. A miss penalty is a time to replace a block in the cache and deliver it into the processor. As for the AMAT, which is the average memory access time, it is the hit time plus the product of the miss rate and the miss penalty. Over here on our right, we have a diagram showing the levels of the caches, as there's a cache level 1, cache level 2, RAM memory, mass storage. Difference between them is that the lower the level of the cache, the higher the bandwidth, and the lower the level of the cache, the lower the latency and sizes. So this is how it averages, as we also discussed last week in our DRAM lecture. RAM memory always falls over, has a higher bandwidth than a mass storage, but it still has a lower latency and a smaller size than a mass storage. Next over here, we'll be talking about cache associativity. There's a direct map cache, a full associative cache, and there's also a SIT associativity. So over here on the right, we have an example just showing the associativity in caches. There's like multiple lines and how they go from one block to another and how they can just interfere with one another going into multiple blocks, multiple caches. A direct map cache it's the simplest cache out there. Each block maps to exactly one cache location. So in this example, cache line 1 directs only to block 0. That is a direct map cache. While there's a fully associative cache, it's a data can be stored in any cache line. No conflicts, but expensive and complex. But this is where it can go into multiple blocks, as shown in our diagram. And then we have the set associativity. It divides caches into sets. And it also, each memory will have its own address map to exactly only one set, and it has more flexible and efficient than just a direct mapped cache. Next over here, we'll be going over some cache misses and performance. There are types of cache misses. There are compulsory, capacity, and conflict. Compulsory is the first access to a block. Capacity is when the cache cannot contain all blocks needed. And the conflict is when multiple blocks map to the same cache location, which, in other words, there's a conflict between one another. As for the cache misses and CPI, misses increase per cycles per instruction. Importance of reducing miss rates for better performance. That's how they relate together, the CPI and the miss rate. Over here, we have a graph showing how the CPI and miss rate interfere with one another and how they pretty much like go on the same rate, and how like they recover from one another, in other words. Next over here, we'll be going over cache optimization, reducing hit latency, reducing miss rate, and reducing miss penalty. If we are able to reduce all of these, we will be able to optimize our cache. Hit latency, reducing that will be like by increasing the number of blocks. The miss rate, increasing it, we need larger block sizes, larger cache sizes, and higher associativity. As for reducing miss penalty, we use multi-level caches and implement hardware and compiler prefetch. Next over here, we have an example and a case study. The example, we have one example, which is given addresses sequences determine the block size associativity and size of the cache. And then once we have that, we can analyze hit or miss outcomes to understand cache's behavior. Another example would be like calculate the overall miss rate for a given code and cache configuration, and discuss the implications for cache design and performance. Over here on our right, we have a just a small cache memory, and it's an organization, and how they are set with one another and described. The logic sends direct interference to the block frame, where over there's data and it has multiple sets, and depends also, it might have like different associativity like we discussed earlier. And from there it can direct to the main memory page and the CPU. Next, we'll talk about the write policies. There's a write through, write back, and a dirty bit. A write through is data read into both cache and lower level memory. It ensures data consistency but has a higher latency. Whereas the write back, data written only to the cache, it's written back to lower level memory when block is evicted. It's not written to both the cache and lower level at the same time. But it's more efficient and it requires additional hardware. So, and when we talk about additional hardware, we mean the dirty bit. So what is the dirty bit? It indicates if a block has been modified. It helps determine if data needs to be written back to memory. So that's the difference between a write back and a write through policies. And over here on our right, we have a small example showing that. All right. Next, we'll be going over the conclusion of this lecture. We just went over our cache design space, balancing cache sizes, the block size and their associativity, their impact on performance and energy consumption, their importance of cache optimization, and their key takeaways, which were understanding cache structure and behavior and applying cache optimization techniques. Thank you, and this will be it for today. You guys have a good day. Bye-bye.